Hey physics, this is the help video for atomic mass and the strong force. So where we're starting at right now is with the nuclear model. So the big thing here is that we have found out that most of the atom is empty space, meaning that all of the positive charge and most of the mass of the atom is concentrated in the super small, dense, positively charged nucleus. Okay, so to give some perspective of how small this nucleus is, if this nucleus was a marble, then the size of the atom as a whole, like where the electrons can be, is the size of a football stadium. And not like Williamston High School football stadium, but like the big house, right? So we have a marble nucleus inside of this gigantic nuclear, inside of this gigantic atom where all these electrons can be, okay? So what we know is that all the positive charge, so I guess I should clarify there, we're not changing the size of the atom as a whole, we're just saying that the nucleus of the atom, where all the protons and the neutrons are, is really small. So all the positive charge in an atom is contained in a tiny dense nucleus at the center of that atom, meaning that these positively charged particles in the nucleus are called protons. Protons have a positive charge and they live in the nucleus. And as we know, positive charges, positive electric fields, hold still. They don't go anywhere. So each proton has a charge of +1. There's the positively charged electric field, just hanging out there in the nucleus and putting out its positive charge. Then we have electrons, which each have a charge of -1. So you can see a negatively charged electric field there. And electrons, in contrast, they do move. And they also they are very, very small, like even smaller than protons, even smaller than the nucleus itself. They're very, very small. And they have a negative electric charge, okay? So protons +1, electrons -1. So they balance each other out. So now that you've got that, let's do some math about it. So this hydrogen atom has 1 electron and 1 proton. So the overall charge, if you have 1 electron and 1 proton, it's going to cancel each other out and it'll be neutral. This alpha particle, which is something you'll remember from Rutherford's experiment, has no electrons and 2 protons. This is a helium atom without any electrons. So 2 protons and no electrons is going to give us a positive +2 charge, right? Okay, so then this fluorine atom has 10 electrons and 9 protons. And I want to tell you about the strategy I use to quickly tell what the charge is going to be. I think about this, like if I was to line up each one of the electrons and each one of the protons, which one would hang off? So if I have 10 electrons and 9 protons, electrons have a negative charge, so that's going to give me an overall charge of -1, right? So negative -1. All right, so this gold atom has 79 electrons and 79 protons. So regardless of how many protons and how many electrons it has, if they're balanced, it's got a neutral charge. So that's pretty easy. Now that you've mastered charges, let's get good at calculating atomic mass. Each proton has a charge of +1, right? But it also has a mass of 1 atomic mass unit. And that is kind of like the basis for all atomic weights, basically, is the weight, this mass of this proton. Okay, 1 atomic mass unit. Electrons have a mass, each electron has a mass of about 1,000th of an atomic mass unit. So like electrons are like 1,000th of the size of a proton. Super duper schmooper tiny. So don't worry about electrons. Sorry about that. Don't worry about electrons when you're calculating atomic mass. They're just too small to even worry about. But there is another particle that we have not talked about yet, and that is the neutron. So the neutron, each neutron has a mass of 1 atomic mass unit also. So protons and neutrons weigh the same. They both have a mass of 1 atomic mass unit, but the neutron's charge is neutral, meaning it is balanced. It is a zero charge on the neutron. So to review, electron has a charge of -1, and the mass is 1,000th of an atomic mass unit. The proton has a charge of +1, and the mass is 1 atomic mass unit. The neutron has a charge of 0 and has a mass of 1 atomic mass unit. So now let's do some atomic mass calculations. So this helium atom has 2 protons, 2 neutrons, and 2 electrons. Think about it. How much atomic mass is that going to have? It's going to have an atomic mass of 4. 2 protons plus 2 neutrons equals 4 atomic mass units. And whenever you're talking about the mass of an atom, you should always put the units there, atomic mass units. And the electrons don't really count for mass. So this carbon atom has 6 protons, 6 neutrons, and 6 electrons. So what's the atomic mass there? 6 protons plus 6 neutrons is going to equal 12 atomic mass units. Don't worry about the electrons. This oxygen atom has 8 protons, 8 neutrons, and 8 electrons. So that's going to have an atomic mass of 16. Protons plus neutrons. Don't worry about the electrons. But wait, with all of those protons so close together in the nucleus, why don't they repel each other and fly apart? Because we know that like charges repel. Like that's what we've been learning this whole time, right? How come those protons in the nucleus can be so close together and they have a charge? I mean, they have a +1 charge that would totally seem like it would make them fly apart. Why don't they? It's because of the strong nuclear force. And this is one of 4 fundamental forces that kind of make the world what it is. So the strong force works at very small distances only, such as those inside the nucleus. The strong force overcomes the electromagnetic force and prevents the electrical repulsion of protons from blowing the nucleus apart. So I like to think of the strong force like the love that keeps our families together in our tiny houses, right? Even when we, might want to have more space all on our own, right? The 4 fundamental forces are the strong nuclear force, which keeps these atoms keeps the protons and the neutrons together in the nucleus. Electromagnetism, which you know about, that's the charges, pluses and minus. Gravity is what keeps very small things close to very big things, or makes them want to be close to big things, like an apple, or like us on planet Earth. We are very small compared to planet Earth, so gravity makes us stick. And then there's the weak nuclear force, which is a very intense topic, and I'm just going to show you the picture and leave it at that. It has to do with radioactivity, and it's about like how radioactivity will happen. But we do not have to worry about that right now. So the strong nuclear force holds the nucleus together. And most of the atoms in our bodies, in the world around us, are pretty small. Like they're things like carbon, which has an atomic mass of 12, or oxygen, which is an atomic mass of 18, or 16. Like small things like that. So the strong nuclear force has no problem holding those things together. And in fact, here's a crazy fact that I think just like blows my mind and kind of puts it all together. The nuclei in our atoms, the protons and neutrons that make up the atoms in our body and like kind of the world around us too, have probably been the same for like potentially billions of years, because the strong force is so strong that it takes a ridiculous amount of energy to break it up. So the amount of energy that would cause a nucleus to break apart is like the kind of energy that happens in an atomic bomb or in the center of the Earth, where like magma is happening and there's crazy amounts of pressure, or like if we're on the surface of the sun, that's the kind of thing that breaks up the nuclei of atoms. But for the most part, the nuclei of our atoms, those protons and neutrons, have been stuck together for probably billions of years, most of them. Electrons are going to fly around. Electrons go wherever they feel like it. They stick wherever it makes sense for them to stick, but the nuclei stay together. So when you will recognize uranium-238. 238 is the atomic mass of uranium. It has a combination of like 238 protons plus neutrons. That's a really big atom. That's a really big nucleus. And at that point, it gets hard for the strong nuclear force to hold it together. And that's why we get things like radiation, because the strong nuclear force is just like stretched so far by that giant collection of protons and neutrons that things want to start flying off. And that's where we get things like alpha particles, trying to make that atomic mass a little bit smaller so the strong force can hold it together still. I wanted to show you a graph. For some people this is helpful. Some people, if it's confusing, don't worry about it. But this is a graph that shows how strong these four fundamental forces are within the scale of an atomic nucleus. So you can see that within the scale of the atomic nucleus, the strong nuclear force is really strong. It's got a really strong attractive force at those very, very small distances. The electromagnetic force is pretty strong for quite a ways, and of course that's going to be outside of the size of the nucleus because those electrons are affected by the electromagnetic force, and they, circle around the nucleus. Then not to scale, we have gravitational force, which works on pretty long distances. Like if you're out in the atmosphere of the Earth, you're still going to fall down to the Earth. And then when the weak nuclear force works at very small distances within. So here's some good atomic math. Here we go. So this calcium atom has 20 protons, 20 neutrons, and 18 electrons. So we want to calculate the overall charge and the atomic mass. So I'm going to do mass first because I see protons and neutrons on top. 20 protons, 1 atomic mass unit each. 20 neutrons, 1 atomic mass unit each. That's going to be 40 atomic mass units, and you can actually see that right here, 40. 18 electrons compared to 20 protons. If I was going to line up those 20 protons and those 18 electrons next to each other, I would have 2 protons that fall off the edge. And that means we're going to have a positive 2, like a +2 charge on that calcium atom, because there's 2 more protons than there are electrons. So that's that. Let's try gold. This gold atom has 79 protons, 117 neutrons, and 80 electrons. Let's do atomic mass first. So that's going to be 79 plus 117. The bigger the atom, the more protons that are in there, then there's like an overbalance of neutrons, just generally. As you get bigger atoms, there's going to be more neutrons to kind of keep it held together, I guess. So 179 plus 117 is going to be 196 atomic mass units. And if we're looking at the charge, I see 79 protons and 80 electrons. 1 electron is going to fall off, so that's going to be a -1 charge for that gold atom. And you can see there's the atomic mass unit there. So platinum is actually right next to gold on the periodic table of the elements. It has 78 protons, 117 neutrons, and 76 electrons. So the atomic mass is going to be 195 atomic mass units, which you can also see down here. Sorry, these are blurry. And then if we have 76 electrons and 78 protons, that's going to be a +2 charge. So here's our challenge questions real quick. How much atomic mass does an atom of americium, which is a man-made element that was created during the intense study of atomic energy and the atomic bomb and atomic nuclear energy and all that stuff? There was like a lot of experimentation done creating new elements. So americium is one of those new elements. So I see it has 95 protons and 148 neutrons. So I'm going to let you do the math on that one. How big is that going to be? And then this is a super fun challenge question. What would you need to know to calculate the charge on this polypropylene molecule? This is a bunch of atoms stuck together, and each one of those atoms could have a charge, but they kind of work their charge out with each other to some extent. So there's a lot you would need to know to find out about the charge on this polypropylene molecule to make this relevant to like the world around us, right? Polypropylene is plastic. You might want to know what atoms are here. We have fluorine, we have hydrogen atoms, we have carbon atoms, 1 oxygen atom, 1 nitrogen atom, and we would need to find out a lot of stuff here, how they interact with each other, what forces are acting on them right now. I noticed that plastic polypropylene tends to attract electrons. So where would it do that? Where are the extra electrons going to be hanging out? A bunch of good questions there. So I'm going to let you go. This is the end of my video, and I hope this was helpful to you. Thanks.